I have to give this talk because my PhD student, Tamer, hasn't been able to get a visa yet. But he did all the work, and I, unfortunately, collect a little bit of the glory. Bugs in cryptocurrency have been expensive. We all know this. And a big source of these bugs has been bugs in smart contracts. And so to try to address that, people have come up with a whole variety of static analyzers to look for smart contract vulnerabilities. These are very impressive tools, but they have some drawbacks. They're difficult to maintain and extend. Would it be possible to reset that timer so that I can keep a track of where I'm going? They're difficult to maintain and extend. They require expert rules because humans have to think about the semantics of smart contracts. Partially as a result of that, they mostly work on source code, basically because the humans find it easier to come up with the expert rules reasoning on source code. And a lot of these static analyzers are slow. They're doing lots of stat solving or other kinds of techniques. And so our research asks the question, can deep learning address some of these challenges? And so we present DLVA, the Deep Learning Vulnerability Analyzer. What does it do? We detect 29 different vulnerabilities in this giant wheel, some of which are more serious than others. And we do this without any predefined patterns or expert rules. We analyze bytecode directly, so we don't need source. We have high accuracy and a low false alarm, false positive rate. We almost always answer yes or no, and we do so between 1 and 3 orders of magnitude faster than competing tools. We're extensively benchmarked, and we're available immediately. So an example of a vulnerability is the DAO attack, or a simplification of the DAO attack. You can think of this as a bank account. You make a deposit, you can make a withdrawal, and the bug is here. And essentially what's happening here is we're sending out the money that's in the bank account, and then after the bank account has been emptied, we zero out the account balance. And the problem is that sending money, or actually receiving money in Ethereum, is a kind of a function call. And so if we send this money, we're actually going to run code in the destination, and that code could do anything. In particular, it could make another withdrawal. And since we haven't yet set the balance to 0, it could withdraw the amount again, and then that itself would trigger another fallback. We could withdraw and withdraw and withdraw and withdraw, and only after we've withdrawn 10 or 15 times our account or 100 times our account do we set the balance to 0. This is essentially what happened in the DAO attack. They stole 3.6 million Ether, which is, I think, about $7 billion today or something like that. So that's the motivation. Next, I'm going to talk about the design of DLVA, a little bit about the training, and then the benchmarking. So how does a neural network work? Well, you have some kind of input encoded as a feature vector, in other words, a vector of numbers. You feed that into some neurons. Those neurons propagate the values to other neurons with various kinds of weights. The propagation continues onwards until eventually you get an answer. And then you evaluate how close the answers are to some expected answers. And if they're not that close, you calculate some loss function, and then you sort of backwards propagate the weights to be closer to the answers you want. And you sort of do this iteratively until you end up with weights that give good answers. And from a technical perspective, the problem is that smart contracts are code, not feature vectors. And so we have to encode a smart contract into a feature vector for this to work. Here's the architecture of our system. I'm going to go through these components one at a time. Before I do that, there are two sort of key ideas. One is that the neural networks are going to learn from feature vectors to classify contracts. And another key idea is that we're using a specialized kind of neural network called a graph convolutional network to extract semantic structure, in particular to extract the structure of the control flow graph. So pre-processing. Well, we start by getting a lot of contracts, about 52 million contracts. There's a huge amount of redundancy, so we eliminate 99.3 of them. That leaves us with about 368,000 unique contracts. We then label the contracts with these 29 vulnerabilities. We use a static analyzer called Slither to do this labeling. Unfortunately, Slither can only label about a third of the contracts because Slither requires source code. So it labels about 120,000 contracts or something like that. And then we extract from the bytecode CFGs. So we end up with CFGs like that. And this is a sort of an important observation, is that we can extract much more understanding of the contract by using this graph structure than we can if we treat a program just as a large list of tokens. So node to vector, what does this do? Well, we start with this control flow graph of basic blocks. We feed it into the universal sentence encoder, and then out the other end pops a graph of vectors. Universal sentence encoder is essentially a neural network for natural language processing or other kinds of processing. It just processes linear data. And the basic idea is that a similar basic block should end up with a similar vector, clusters of vectors. You can kind of think of it like that. So our smart contract to vector engine, what does it do? Well, it takes this graph of vectors, we feed it in, and out pops up a very long, flat vector. For most contracts, for large contracts, it's a 4,000 dimensional vector. The key idea here is that we use these graph convolutional layers, that's that box there on the left, to make these summaries. This is an idea that I think originally came from image processing, where the importance of a pixel is not just the value of the pixel itself, but also the value of neighboring pixels. And here we have something similar. The importance of a basic block is not just the block itself, but also the blocks it's wired next to. And again, our goal is that similar contracts should be clustered to similar vectors. Now that we have our enormous vector, we have two relatively simple ways to try to classify them. We have a sibling detector, and what this does is it looks for, we have a contract we want to evaluate, we turn it into a vector, and then we see, is there a contract in the training set which is close to this contract? Euclidianclose. In that case, we give it that label, vulnerable or non-vulnerable. If there's no close contract, we call it unknown. In that case, we call this core classifier. This is a feed-forward neural network, and it essentially extrapolates the contracts to try to guess a label. Okay, so that's the basic design. Let me talk briefly about training. We have three neural nets here. We have the node to vector net at the top. We have the smart contract to vector nets here, and then we have the core classifier here. The node to vector we train by giving it 22 million basic blocks from our data set, and it's essentially an unsupervised training, so that's all we give it. The smart contract to vector and the core classifier are trained together on 72,000 contracts. And what this means is that instead of one smart contract to vector engine and 29 different core classifiers, one for each vulnerability, we actually have 29 pairs of smart contract to vector and core classifier. And these are trained in a supervised fashion using the labels that were given by Slither. Slither only labels source code. So one key idea here is that we are training a bytecode analyzer using a source code oracle. And now I will briefly talk about benchmarking. So benchmarking is difficult. There are very few data sets out there that are of decent quality. You'll notice we have 5 different data sets here. And the 2 data sets that have the most vulnerabilities, the problem is that how do we know whether something is true or not? Well, we've asked Slither, but Slither also has mistakes. So, our sort of confidence in that is lower. The lower 3 benchmarks, we establish truth in a more objective, independent manner. But they're much smaller because a lot of them are human verified and that kind of thing. All these data sets are, of course, disjoint from all the training data, so we're not like looking at the exam while we're studying. And all of the data sets are publicly available. And I'm just going to talk briefly about benchmarking on these 3 down here. Even though they don't have very many vulnerabilities, they're the data sets that we think are of the highest quality in terms of we trust the labels the most. We've benchmarked ourselves against 9 competitors over the last 6 years. Almost all these competitors are based on static analysis. Almost all of them are based on source code rather than binary. And as you can see, although there are 2 that do more vulnerabilities than we do, we still do a fair number of vulnerabilities compared to the average. So when you're trying to evaluate something like this, there are 3 statistics that you might care about. One is the true positive rate. In other words, how often we correctly identify things that are vulnerable. And in this benchmark, we were 3rd best with 98.7%. So 2 tools beat us. You might also care about false positives, and people who do software engineering or who do code practice, if you want to deploy something for developers to use and it starts raising lots and lots of false alarms, developers are just going to start ignoring it. So one of our advantages is that we are 2nd best with only 0.6% false alarms. And so then the overall score is accuracy. In other words, it's the total number you got right. And although there are tools that have better true positive rates and there are tools that have better false positive rates, overall we balance them the best. So our accuracy is 99.7, which is the best of all. 2 more statistics. The completion rate is the percentage of queries that we answer. And in particular, that means that we don't time out, we don't raise exceptions, we don't consider a contract to be out of scope, all of those kinds of things. And essentially, our completion rate is 100%. The only way we don't give an answer is if we fail to build a control flow graph, which is very small percentage. And you might also care about time. This last graph is in log scale, not linear scale. Again, we're at 0.2 seconds, which is between 1 and 3 orders of magnitude better than the competitors. So overall concluding thoughts. Neural nets are surprisingly good at understanding smart contracts. Incorporating some semantic understanding, the idea of control flow graphs improved results. It's very hard to pin down why something is flagged. So if you've never used a tool like this, it sort of at the end says, this smells funny. And it's a really good nose, but it can't explain more. Finding good data sets is tricky. Our performance is essentially in real time. And our tool is available for immediate use. Thank you.